In this video, I'm going to introduce an application of linear transfers used a lot in robotics. First, let's define our robot. In this picture, we have a two-axis robot. Two-axis means it has two motors that help control the motion of the robot. And we have an end effector. That's the grippy part that picks things up off the ground. And so this two-axis robot can rotate around the first motor, and that rotation is in the clockwise direction. We're defining the coordinate system as X along the bottom of the screen and Y up the side. And then the rotation in the clockwise direction actually rotates in the Z direction, which is into your screen. The second motor also rotates in the XY plane in a clockwise direction. And between these two motors, we can get all kinds of motion. For example, if we move the second motor up or in a negative direction, so A2 would be a negative number, that would make it go counterclockwise up. And then we could turn around and move the first axis in a positive clockwise direction, which would move not only the end effector, but the second motor down together. And so in order to define the kinematics of the system, we have to define some coordinate systems. So the first coordinate system I want to define is down at the base of the robot, underneath the first motor. That coordinate system is called the world coordinate system or the ground coordinate system. It doesn't move. No matter what the motors do, that coordinate system stays affixed to the ground. Our second coordinate system is at that first motor, and it's going to move with the rotation of that motor. And the third coordinate system is at the second motor, and it's going to move with the second motor's rotation. So it will rotate with the second motor. And then finally, the end effector is where we actually care the most about, which is where those gripper is going to pick up something off the ground. And it's really the transformation between the end effector and the world coordinate system that we care the most about. We want to maneuver the robot into a location so that the end effector can pick up something in the real world. We need to be able to program that. So in order to define these, we need to define a bunch of variables. In this case, we have the two rotation variables, which is A1 and A2. And we also have some offsets. D1 is the distance between the ground coordinate system and the motor 1 coordinate system. D2 is the distance from the motor 1 coordinate system to the motor 2 coordinate system. And DE is the distance between the motor 2 coordinate system and the end effector. So hopefully you can see that, and let's do another example. So if we were to rotate the second motor, you can see that the end effector would rotate and both coordinate systems would stay in line with each other, but they would be rotated relative to the ground truth, the world coordinate system. And so when we rotate the first motor down, you can see that all three robot coordinate systems move with it. The ground coordinate system stays the same. So let's define a transformation from the end effector to that second motor's coordinate system. And if we look really closely, we can see these two coordinate systems are parallel to each other. The x directions are collinear, the y directions are parallel, and the only real difference between them is the origin, which is an offset of that distance dE. So it's pretty easy to come up with some equations that just take any point in the end effector's coordinate system, like an xe, ye, and then translate it and define it as a point in the second motor's coordinate system, where you're just adding that distance dE to the xe coordinate. Now, one thing we're going to do here is we're going to translate those equations into a matrix form. This is the same set of equations. You might want to multiply them out just to make sure you see that they're the same. The only thing we did was we had a third equation that says 1 equals 1 times 1, which is obviously correct. And that allows us to make a square transformation matrix, which is important in this case because what we want to do is be able to invert them. The square matrix allows us to do that. And so this set of equations is exactly the same as the first set of equations. It's just now in a matrix format that is nice for the kinematics. I actually care most about that middle matrix, which is the JE transformation matrix, which transforms any point in the end effector's coordinate system into the second motor's coordinate system. When we rotate that second motor axis, we now want a transformation matrix that goes from that second motor's coordinate system down to the first motor's coordinate system. And that has to include somehow this rotation. And rotations by themselves is not too hard. So we can rotate around a point pretty easily. We can say that that second motor's coordinate system is rotating about a axes that is on the same origin, but collinear with the first motor's coordinate system. And so that rotation is very simple. It's just our simple rotation matrix. And so we can take our second motor's coordinates and rotate them to this new vertical coordinate system. But then what we need to do next is translate the whole coordinate system down to this first motor's location. And we can do that transformation just by using that D2 distance value, and we can just tack it on as an addition in the y direction. So now you see this system of equations represents the transformation from the x2 coordinate system down to the x1 coordinate system. And we can rewrite this again as a 3x3 matrix. And I suggest you take a little bit of time to multiply both of these matrix equations out to show that they actually are showing you the exact same equations. And really, again, all we really care about is that middle transformation matrix, which we're going to call J2, which is the rotation around A2 and then the translation down to that first motor. Finally, we want to look at that first motor's transformation and get it to transform down to the ground or world coordinates. Coincidentally, this is pretty much the exact same math we just did. Instead of going to from motor 2 to motor 1, we're going from motor 1 to the ground. So the transformation matrix is using an angle of A1 instead of A2, and the distance now is not D2, it's now D1. But other than that, these two matrices are exactly the same, but we're going to define this matrix as the J1 matrix, and now we have everything we need. We have defined the JE matrix as the matrix that can take us from the end effector's coordinate systems to the second motor's coordinate system. And then we have another matrix, J2, which can take us from the second motor's coordinate system to the first motor's coordinate system. And finally, we have a transformation, J1, which takes us from the first motor's coordinate system down to the world coordinate system. And I hope you can start to see that we can put these into next to each other. The output of one of these equations turns out to be the input of the other equations. And so we can just stack them together and create one big equation. So if I take the end effector's coordinate systems, left multiply it by the JE transformation matrix, then left multiply the result of that by the J2 transformation matrix, and then multiply the result of that by the J1 transformation matrix, I should get our world coordinate system. And if you think about it, J1, J2, and JE are all 3x3 matrices. So when we multiply a 3x3 by a 3x3 by a 3x3, we still always end up with a 3x3 matrix. So all the transformation matrix can be summarized in one 3x3 matrix. What's really neat about these matrices, and there's a proof that I could probably show you later, that they're all invertible. And so what that means is if I take the J1 matrix and invert it, I can multiply it by points in the world coordinate system and get those same points in the first motor's coordinate system. I can multiply the inverse of J2 by the coordinates of the first motor and get coordinates of the second motor. And I can multiply the inverse of JE by the second motor's coordinates and get the end effector coordinates. And so basically I can do the reverse. I can get all the world coordinate system through a transformation matrix, and it will give me the end effector's coordinate system. So hopefully you're starting to understand how these transformation matrices work. They're a really powerful thing in robotics, but we use exactly the same math when we're doing computer graphics and a lot of other 3D manipulations. And so I hope you found this useful.